Hi, this is Alex from the University of Tours. Today I'll be presenting a joint work between our research group and Stefano Rizzi at the University of Bologna and Panos Vassiliadis at the University of Ioannina in Greece. This work is titled The Traveling Analyst Problem, a Definition and Preliminary Study. In a previous paper, Panos Vassiliadis and Marcel introduced intentional OLAP with the goal to replace the more traditional querying of data cube with a much more intuitive way using the user intentions as in place of queries and using data story in place of results. This approach focuses on finding so-called insights inside the data and presenting them in a meaningful way to the user in a way that also answers the original intention of the user. And those insights, they will relate, as we see later, to interestingness measures. In this work, the main problem we want to tackle is telling coherent story from a large amount of data. The first issue with this is that we need to find the best queries, and we need to order them in a specific way so that the story has some sort of a meaning. We also want to know if the results of those queries are relevant to the story and are interesting, and it would be even better if we could do this before we execute the queries. And of course we don't have all the time in the world. We have a specific time budget, somewhat short, a few seconds, that is specified by the user, kind of like automated machine learning, but probably even shorter budget, so on the order of seconds, not minutes or hours. So intuitively, we start from a set of queries which represent a reasonable, explorable subset of the search space. A function of interest, estimating the interestingness for a query. A cost estimate function estimating the execution cost of a query. This can be, for example, fetch from a DBMS optimizer, and sort of a cognitive distance between the results of queries. So basically looking at the strain you put on the user who is reading the story when he moves from one visualization to the other, and he has to change his mind about measures, about the projections, about filters, etc. And we want to find a sequence of queries without repetition that maximizes the overall interestingness and respects, of course, this budget in time, and the order must minimize the overall cognitive distance between the queries. So this is a strong NPR problem. There is a small proof in the paper. It's multi-criterion optimization problem. It's sort of a mix between the knapsack problem and the TSP problem. So basically the knapsack looks at this interestingness versus cost in time, and the knapsack and the TSP looks at the cognitive distance and the optimum order. And this is kind of a new problem. There is a lot of variance in operational research of TSP and knapsack. This is a new variant that's a mix of the two, not previously studied. So practically, you have to start from, as I said, a set of candidate queries. There is a lot of way to generate them. A simple example is to start from a seed query that represents the initial intention of the user and to perform simple roll-up, drill down, and filter change, so-called sibling queries on it. In this first study, we use pre-existing interestingness, cost estimate, and distance, cognitive distance functions, but of course they can be swapped for another one without problem. So we present three resolution methods for the problem. Of course, there is the brute force approach, which is extremely complex. You can show that it has a n factorial time complexity over the size of the starting set cube. You have the naive heuristic, which is first you solve the knapsack on the interestingness versus cost estimate, and then you solve the TSP over the order and you execute everything. And there is what we call the ReOpt heuristic, which is inspired by reoptimization schemes in classical DBMS optimizer, where we will first we generate an initial query plan running the knapsack once, and then we start executing the query inside the plan, and one by one we will execute the query and check how are we doing with our time budget. And there is two possible scenarios. Either we are over budget, so basically we have consumed more time than we expected, and we will have to remove potentially queries from the plan, so running again a knapsack algorithm there. Or we have more time than we expected, and we also run a knapsack algorithm, but this time we will look at all the queries in queue, possibly to add them within the remaining extra budget that we have. Once we have completely depleted the queries to run or the time budget, we will then move on to ordering the queries, running TSP, and presenting the result to the user. So the implementation is basically done in Java 12 to take advantage of the Mondrian rollup server, which is completely open source. And we did the tests on a simple laptop with a 1 GB SSB cube, so basic SSB cube, and a real cube that has way higher dimensionality but with less facts on French households and their vulnerability to energy cost.
First experiment, look at optimization time versus size of the input problem. It's done on the SSB cube. As you can see, the exact solution takes exponential time to produce, because we are looking at a logarithmic time scale. And the K plus TSP, or so-called naive heuristic, is quite fast. Looking at our ReOpt heuristic, it's a bit longer, but it's completely under control. It doesn't go into second scale optimization, and it still takes longer because we have to execute multiple times the knapsack solver during the execution, so it has to be longer than the naive solution.
Next result, we move to the real data, and we look at the naive heuristics versus the ReOpt heuristics in its ability to generate a big interestingness score. So the expected behavior was we take advantage of the time left, so we get more interestingness in the end, and this is verified. And the last, again on the French energy cube, result is that basically we confirm that why we have better interestingness. It's because our ReOpt heuristics will basically explore the entire search space of the seed queries if it's given enough time budget, and it will overall waste the percentage of unused time is always less than the naive heuristic. So basically we don't waste time, and we take this time to explore the search space as much as we can, as long as the budget is high enough. So in conclusion, we define the first step, basically the core algorithm that will allow us to design automated exploration of data sets, implementing this intentional OLAP paradigm. And well, our perspectives are to, of course, maybe generate a more interesting set of candidate queries, maybe generate better cost, interest, or distance function using machine learning, specify a language, high-level language, or maybe a translation from natural language to express this seed query, and much more. We have the OLAP 3 website that you can visit, and you can stay tuned in to the Blobfish research channel for upcoming research. And of course, you can always ask questions using our email addresses on the screen right now. Thank you very much for watching this special edition of Online OLAP, and I hope to see you all in person next year for the next OLAP. Thank you.